Okay, welcome back. So today we're going to talk about linear independence. I just realized this chapter number is wrong, but that is okay. This heading is correct. We are going to talk about linear independence. And this is something that has really been going on in the background of things we've already done, but you may not have picked up on it. So we're going to spell it out formally. So we'll start with a definition. So a set of vectors is linearly dependent if we can express the zero vector as a non-trivial linear combination of these vectors. So let's break this down. A linear combination is some constant times the first vector plus constant times the second vector, etc. So we're saying some linear combination. Multiply them by constants and add them up, and I get 0 for every element. Okay, so when I say a non-trivial linear combination, what I mean is that all of these constants are not 0, right? Of course, any set of vectors, I can multiply by 0, add them together, and I will get 0, right? That's trivial. So I'm talking about a non-trivial linear combination. And then the converse of this is that a linearly independent set of vectors is such that this equation here, this linear combination, has only the trivial solution. So the only way I can get 0 by adding them together is by multiplying them by 0. Okay, so here's an example. I have 3 vectors, and these vectors are linearly dependent because if I add 2 times v1 plus v2, so that would be 2 plus 1 is 3. 2 times 2 is 4, plus 2 is 6, and 4 plus 3 is 7. So V3 can be written as a linear combination of V1 and V2. That's one way to write this. Or I could write that 2V1 plus V2 minus V3 is equal to 0. This is a linear combination. It's non-trivial, because these are not all 0, right? It's 2, 1, minus 1 are my constants. Linear combination equal to 0. So this is the formal definition of linearly dependent. But oftentimes this is how we think about it. We think about one variable is redundant because it's really just a combination of 2 others. I don't need this one. It's explained exactly by these other 2. And so this is what we call perfect multicollinearity. I'm sure that you've heard that from Dr. Labar's portion when he speaks of regression, right? Perfect multicollinearity is a very, very bad thing. In fact, it completely violates the assumptions of regression. So using those same vectors, we pointed out that 2 times v1 plus v2 would give me v3. But, and maybe you can see that if you looked at these long enough. But maybe, what if they're longer vectors or they have decimals and it's more difficult to tell? How can we tell if these vectors are linearly independent or dependent? Well, we have to ask the question, and we want to know if there are coefficients, alpha 1 through alpha 3, such that this linear combination is going to give me the 0 vector. Well, all that is a linear system, right? Anytime I have a linear combination of vectors, what I really have is a linear system. And so I can write that system out. I have V1, V2, V3, create the columns of the matrix, and then I have my coefficients, alpha 1 through alpha 3, and I set that equal to 0. And so I can proceed and solve this using Gauss-Jordan elimination. And if I were to do that, I would find exactly the solution that I found on the previous slide. 2 times V1 plus V2 minus V3 would give me 0. So that's how I know that these are linearly dependent, not independent, but dependent. So if the only solution was the trivial solution, if I were to work through the same example and find that alpha 1, alpha 2, and alpha 3 must be 0, then I'd know that those vectors are linearly independent. Here, there should be a comma here. Apologize. Okay, so what would that look like if I know that all the coefficients must be 0? Well, it would mean that if I did Gauss-Jordan elimination, the matrix would end up being the identity matrix, right? Because my right-hand side here is 0. And so I would have to have the identity matrix on the left-hand side. So that means I have no free variables. So again, in summary, that sum from that definition where we have the coefficients times the vectors added up equal to 0. All this is a matrix vector product, and I hope that by now you can see that, because this is a very common thing that we're going to use when we get to the MSA program and we are talking about linear algebra and a lot of data analytical techniques. We have to realize that linear combinations can be written as matrix products. Okay, that V matrix, and I'm not sure if we've seen this notation before, but what this means is just we're going to create a matrix with these vectors as columns, just like we did on the previous slide. Okay, so I'm creating a matrix from column vectors. And this alpha vector is my vector coefficients from my linear combination. So all we need to do is determine whether this system of equations has any non-trivial solutions. And so if a set of vectors, and when we talk about vectors, for the most part, I want you to think variables. If that set of variables is not linearly independent, then the matrix that contains those vectors as columns, well, that would be our data matrix, right? Our data matrix has variables as columns. So if those variables are not independent, then the data matrix is not full rank. Remember that the rank of a matrix, or I'm sorry, don't remember this, but you're learning it now. The rank of a matrix can be defined as the number of linearly independent columns or rows in that matrix. So before we talked about the rank being the number of pivots. Well, it turns out the pivots are what's counting these linearly independent columns. Because whenever we can zero out a pivot position and zero out a complete row of a matrix, what we're really doing is taking linear combinations and of the rows, or, well, in our situation it was the rows, taking linear combinations of rows and getting 0. So by very definition, when we get a complete 0 row, that means that the rows of the matrix are not linearly independent. So the rank of a matrix is the number of linearly independent columns or rows. It's the same as the number of pivots. And it's always going to be the case that the number of linearly independent rows is equal to the number of linearly independent columns. And in most data applications, the number of rows is going to be greater than the number of columns. So if our data matrix is n by p, where n is the number of observations and p is the number of variables, then the maximum rank that data matrix can have is the number of columns. So it's full rank if the rank is equal to p, the number of columns. All of undergraduate linear algebra, or a significant portion of it anyway, aims at teaching students about the following theorem. And this theorem is about square matrices, matrices that are n by n. And in data applications, we're going to deal with a lot of these types of matrices. So correlation matrices, covariance. In the normal equations, that x transpose x matrix, that is also square. And so what we learn about these is that the following statements are equivalent. So if one of these statements is true, then all of these statements are true. A has an inverse. A is full rank, so the rank of A is equal to n. The columns of A are linearly independent. The rows of A are linearly independent. The system AX equals B has a unique solution. So we can see this because if the inverse exists, I can multiply both sides by the inverse, and I'd find out that x is equal to A inverse B. And that's the solution for x. So this system, no matter what the right-hand side vector B is, will always have a unique solution. Also, if Ax equals 0, then it must be the case that x is equal to 0. Remember, just from a few slides ago, that when I write Ax, what it means is I'm taking a linear combination of columns of A. So if I'm setting that equal to 0, I'm saying there's a linear combination of columns of A that's equal to 0. Well, the columns of A are linearly independent, so it must be the case that those coefficients, that x vector, is also equal to 0. You can also say that A is non-singular. It's another way to say that A has an inverse. And if I perform Gauss-Jordan elimination to the matrix A, the result is going to be the identity matrix, because I'm going to have a pivot in every row and column. So here's a place where you can check your understanding. I have two vectors, A and B. I want to know if they're linearly independent. I want to know the rank of the matrix, capital A, that has the columns A and B. And I also want to determine whether or not this vector 1, 0, 1 is a linear combination of those two vectors. So you can pause the recording now and complete that. And what you should find is that, yes, these two vectors are linearly independent, because the equation, the linear combination equal to 0 has only the trivial solution, where alpha 1 and alpha 2 are equal to 0. Therefore, we know that the rank of the matrix A is equal to 2. It is full rank. And then to determine whether or not this vector 1, 0, 1 is a linear combination of the vectors, all we have to do is write that linear combination as a system of equations. Again, in fact, this is exactly the same type of situation you should have set up for the first one, where we had the vectors on one side and zeros on the right side for the first part. And now we have this vector 1, 0, 1. And you'd find that that system is inconsistent. So no, it's not a linear combination of these vectors. So why do we make such a big deal of this? Well, for one thing, if our design matrix X is not full rank, then the matrix from the normal equations, X transpose X, is also not full rank. And that means it does not have an inverse. And that means that the normal equations do not have a unique solution, which means that our betas are not uniquely determined. There's infinitely many solutions. And so if you ask a software to give you an output in this type of situation, the error that's going to be returned is that your matrix is not full rank, because this is perfect multicollinearity. And that's breaking a fundamental assumption of ordinary least squares, or multiple linear regression. What's interesting, though, is that we'll often run into a situation where variables are linearly independent, but only barely so. So let's look at an example of this. Here I have two vectors, x1 and x2. And I want to solve a system of equations, beta 1 x1 plus beta 2 x2 is equal to y. So I have this target variable y. Well, it turns out this has a nice, easy solution. Beta 1 is equal to 1, beta 2 is equal to negative 1. So x1 minus x2 is equal to y. And you can verify that pretty quickly. Okay, so this is a nice system of equations. It has one perfect exact solution. Now, what happens if I change that system just a little bit? So I take this second part of y and I change it to the third decimal place from 0.067 to 0.066. All of a sudden, that exact solution, which was 1 minus 1, changes drastically to beta 1 equals negative 666. That should be a bad sign right there. And beta 2 equal to 834. Okay, so not only have these parameter estimates changed sign, but they've also changed drastically in magnitude. So you can see this is a problem. You can see that x1, the ratio of the x1 elements to the x2 elements, looks pretty close. And if you were to actually work it out, you'd find that these are almost linearly dependent, except for the fourth or fifth decimal place. So you have two things that are very close to being linearly dependent. So this system is unstable because the columns of the matrix are so close to being linearly dependent. When you have a situation like this, you can notice from some symptoms. You'll see large fluctuations or flips in signs of the coefficients when a collinear variable is added into the model. You may see changes in statistical significance when you add variables in. And the overall f-test might show significance when the individual t-tests do not show any at all. So these symptoms are bad enough on their own, but the real consequence is that behavior that we saw in the previous example. Just a very small change in that underlying system can produce dramatic changes to our parameter estimates. It's really difficult to trust our results. So that is the end of today's lecture. I hope you have a nice day.